Hello, welcome to my channel. In this video, we are going to be solving problem under angular momentum. And the problem we are going to be solving has a diagram of this form. And the question that arises from it is given below. So if we have a uniform rod of length L and mass M and is released from rest, that's this point, in the horizontal position, what will be the speed of the rod when it reaches lowest point, that's this point, ignoring friction at the hinge? So to solve this problem, the first thing we consider is the length, L, and the mass of this particular stuff. Because it is uniform, then the weight will act at the center, which is giving us mg. So the weight is mg. So to solve this problem, we consider the conservation of energy formula, which is giving us the potential energy plus the kinetic energy at this initial points is equal to potential energy and kinetic energy at this final point. So once this one has been established, so at the initial point, the potential energy here is mgh, while the kinetic energy at this point is 0, because at this point it is stationary. The potential energy at this point is 0 because it's at the lowest point, right? While the kinetic energy here is not the usual kinetic energy, which is equal to half of mv squared. It is the kinetic energy of a rotating object, which is giving us mgh plus 0 equal to 0 plus half of I omega squared, where this our I is the moment of inertia of this particular rod. So this is the kinetic energy for a rotating object, right? So our h here, which is from this diagram, can be seen to be L over 2 because the weight of this object is acting at this point, which is more or less like the center of gravity. So when it gets to this point, the height traveled by this point to this point is just from here to this side, which is L over 2. So our h now will now be replaced by L over 2, and our I here will be replaced by the expression for the moment of inertia of a rod, and that is given by mg L over 2 equal to half our moment of inertia for a rod is given by 1 over 3 ml squared omega squared. So if we simplify this one by cancelling ll 2, it reduces to g equal to L over 3 omega squared. At this point, we can make omega the subject formula. We have omega squared equal to 3g over L, followed by w, which is omega, equal to 3g all over L square root. Our omega here is the angular velocity. And if you take a look closely, you'll notice that this particular formula looks like the formula for finding the angular velocity of a simple pendulum. Okay, so now the linear velocity at the middle is different from the velocity at the end of this rod. What this means is that this angular velocity of this rod at any point is the same. The angular velocity is the same. But the linear velocity at this point is different from the linear velocity at this point because of it. The linear velocity depends on the radius or the length of this particular stuff. So first, let's calculate the linear velocity at this point. So to calculate that, we use this formula, which is V, which is linear velocity, is equal to omega r. And our r here is L over 2. So now that we have W, we can replace this W as square root of 3g all over L here, multiplied by L over 2. That will give us the linear velocity. So we have V equal to L over 2, square root of 3g all over L. Then, because our L here can go in, it goes in as L squared. L squared will cancel this L, leaving 3gl, and we have half of 3gl. So this is the linear velocity of the rod at the center. Right? Then let's consider at the point, the tip, that's the bottom. So we have V will be equal to WL because this one is a full length. And when we replace everything, W is already this expression. We have V equal to this. So this is the velocity at the tip. So linear velocity at the end of the rod is given by this expression. So we can see that there is a difference between the linear velocity at the tip and at the center. So this one is greater than this particular one by half. I hope this helps. Please like, share, and subscribe. Thank you.